This is the Winter School 2021, and this presentation is for Asphalt Quality Assurance, what's new. And that picture that I'm showing there is for me working from home, actually, since March last year. Now, the most important problems we see in the field are two. One is rutting, and for rutting, you can see the wheel path right there, and then the rutting is actually the depression under this wheel path. If it's depressed like that with no lip, then most probably is that the base or the subgrade are weak. And this is a more serious problem for rutting than if you have a lip. If you have a lip in here, that means that the problem is basically in the top layer, and that's easy to repair. Rutting could be as severe as this picture in the wheel path, more severe in here, and it could be measured by a straight edge and then measured the depth of this path. Second, or the other most important problem is cracking. There is a lot of cracking happening in the road. One of them is fatigue cracking, which is also on the wheel path of the vehicle. And there is block cracking, there is a cracking, edge cracking, deep cracking. There is a lot, but the most important to us right now is where the vehicle are passing, and that's where you find our cracking. Most distress problems you see in the field could be identified by two parameters, and any distress survey has two parameters actually classifying the road under different levels. One is the severity of the problem, how severe that problem is. Is it deep enough in the pavement or not? And the extent of this problem, how extensive it is along the road. Is it local, or is it among 50% of the road and each location, or all over the road? Here is fatigue problem with high severity and high extent. This is low severity, low severity, no extent almost, and this is caused actually by water damage, whether it's heave load problems or actually water up underneath the pavement itself. They used to use a method called Marshall method of mix design to guard against these two problems. And the Marshall method of mix design is nothing more than this machine here, and we took samples from the road, or even before, if you want to make a design, we fabricate these samples and then put it under this machine. See, this machine has some plates to confine the lateral displacement of the sample. So the sample actually fails by plastic deformation, and that's all what this method is all about. We draw curves from the specimen and the density. So we have the stability, we have the density, we have the air voids, we have the maximum stability, that's the asphalt content underneath it, that's maximum density, that's the asphalt content underneath it. 3% of the air voids, that's the asphalt content underneath it. These three values, average them up, and come up with something called optimum asphalt content that I'm going to put in the road plus some tolerance, because whenever you construct the road, you cannot follow exactly the optimum asphalt content, so do plus or minus. That method was discontinued by Federal Highway Administration in the past few years, and the main reason is the additives that we add to the binder itself, to the asphalt cement itself, like cyclogen and so forth, or the admixtures that we add to the mix itself, to the mixture itself, or we add some co-mixture like grass and grass. So those three components here annihilated the asphalt, the Marshall mix. So it's no longer in the spec. And the main target is to balance rotting and crack in a mixed design. Because if you do that, that would be a key to a long-lasting pavement. But the problem is we have to think outside the box and get some innovation to do that. So what's the innovation? It started with the ALF, Accelerated Load Facility, done by Federal Highway Administration, and it's nothing more than a big load facility where an actual tire goes on top of these pavements that they construct back and forth in a repetitive way, and then they start measuring cores, taking cores, and measuring the behavior or the performance of these cores with time. And they made specifically part of this pavement to fail in rotting and another part to fail in petty crack. To the astonishment that we were thinking all the time that the crack starts at the top and propagates to the bottom. But when we take some cores with a lot of pavements in, with a lot of thicknesses in here, they found out that, and they put it under the microscope on the X-ray, and then what happened is they found out that the crack actually starts at the bottom and propagates to the top. So what they did, a lot of equipment, a lot of testing, because a lot of states start participating in the innovative design, and you see that testing, bending, being fatigue, and that shows the bottom up correctly. And you can think about it this way: if you have a beam and you load that beam, where is the tension? The tension will be at the bottom. So the crack most probably will appear at the bottom and then propagate to the top. And this is again bottom up. Texas came up with their own equipment in here, and this is the semicircular bending machine, and that could do both bottom up or top down, and then the indirect tension or the cylindrical testing machine, and this is for circular fluid. Most of these are basically for cracking. Another equipment like this is called the Hamburg wheel cracker. It's basically for rotting. And what's going to happen is a simulated of the ALF actually, but with very small scale. You have also a load that passes back and forth over the pavement and measure the right depth with time accordingly. And there will be a threshold limit there that if we didn't exceed it, and it forces us to see what's happening in there, you see the distribution of the aggregates is pretty good still and still intact, we end up with some good roads like this. But look here, big problems if we exceeded the threshold and we start designing the pavement below the threshold value, we end up with roads like this. The problem with the Hamburg machine, why we don't use it, is a very expensive machine, and it takes a long time to perform the test. Take that and do a simple test, which is a Marshall tablets, and we put it under load from the top to the bottom. See, there is no confinement here, so it may crack, or generally it will fail more than it will crack. Fail, that means like by deformation. And then we draw the curve, or something called the ideal CT test. And the curve is goes from 0, point 1, point 2, point 3, up to the point 3. Actually, there is no failure per se because of the stored energy in the mix. So up to this point, this is the stored energy in the asphalt mixture itself. And then from that point on, this stored energy is dissipated until failure. Failure or maximum load happen here, but actually you start seeing it in the pavement right there until the pavement is actually completely fair. If we take that and actually put it into a diagram, same thing, load versus displacement, and the same thing until the point of failure, which is going to be 100%, and then we measure at 85, 75, and 65% from the beginning. And the most important thing in here is the slope of that curve at 75%. The slope of that curve, of that line in here, actually discriminate between the different behaviors of different people. So they take this as the most important test right now to characterize earthquake. And he said the area under all this curve is called the fracture energy. But it is not really a fracture, it is a failure energy. It's not fracture. When you start looking at the fracture, and that is the actual fracture testing, is you take the same Marshall stability samples with two wedges and initiate a crack, and you start loading this two wedges in here, and the cracks start propagating. So you measure when the crack reaches 10 millimeter, 20 millimeter, and what's the priming there, and so forth. And that's the actual test method that actually measure the fracture of a static feature. Method, which is the energy under the curve of this curve, not this one. I mean, the curve that is developed in the testing method is called C-star line integral. And actually, who came up with that method 20 years ago was Osama Abdul-Shafi, who was my brother during his PhD. And then lately, University of Arizona, with a Professor Camille Kalouche, who was our student at OSU at that time, liked that method and started investigating it with finite element and so forth, and came up with a procedure for C-star line integral. This is the C-star, and this is the delta displacement per minute. And you can see this is the red dots here as the control. Like here, on top is a rubber mix, at the bottom, polymer mix, and at the bottom here is rubber mix. And you can see that from the control, the polymer mix is far different than the rubber mix. These are more details. I come to the end of my presentation. And if anybody has a question, you can ask. And I'm just going to put these two pictures in there, the power of knowledge. And I like this picture, so I put it there. And then that line saying, if you take me down, when I'm down, you get up pray, I don't get up. Anyway, so that's the end of my presentation. Thank you very much.